Hey guys, Roche here. Right? Okay. So this document covers linear regression. Alright. So the first thing you guys have to do is collect some data, some real life data, and we know that things aren't always in a perfectly straight line. So then you'll have to identify the explanatory and response if you're doing it by CAS. Okay. So the example goes for this one. It goes X for explanatory, Y for response, and it goes 1, 10, 2, 15, and 3, 18. Now, of course, you can have more values than that normally. To get a scatter plot, we go Control I, add data and statistics, and then we go explanatory on the bottom, response on the Y, okay? And to get the linear regression equation, we do this, alright? So that gives me an equation. What's that value again? Y-intercept, and this one is the gradient, or the slope, okay? Does it make sense that the gradient is positive? Yes, it's going up, okay? So, going back to that thing there. So you plot the points and you get something that looks like that, response, explanatory. Use CAS to find the equation, y-intercept plus slope times explanatory. So response equals y-intercept plus slope times explanatory. And then we can use that equation to make predictions and interpret the intercept and slope. So first, the y-intercept is the initial amount, or you would say the LSR predicts that when the explanatory variable is 0, the response variable would be whatever that y-intercept value is. Okay? Now, would that be an example of interpolation or extrapolation? Extrapolation, because if you look back at the data set, alright, x is 0 is not within that data set, so it's outside of that, so it's extrapolation. Okay, so that is the y-intercept, and now we have the slope. The slope tells you, okay, so the slope, the way that you write it out is you say, on average, the response variable increases or decreases, depending if it's positive or negative, by whatever units it is, whatever the slope value is, for every 1 unit increase in the explanatory. That's one way of writing it out. Alright? Example, on average, the response increases by 4 units for every 1 unit increase in the explanatory for this simple example with 3 data points. Yes? Okay. We've already got the line, we fitted it to our CAS. Okay. You can find the least square regression line, which you've already plotted. Alright, and then we can use that to make predictions. Alright, so for example, find the predicted value when the explanatory equals 3. Alright, we've already got that this is the equation. So to find the predicted value, we would sub in 3 for the explanatory. You get 6.33 plus 4 times 3, which gives you 12, which gives you 18.33. Is this interpolation or extrapolation? It's interpolation because 3 is within your original data set. Okay. Extrapolation, you can again predict things outside the data set, does not mean it's going to be reliable. Okay, so again you can substitute in, say, the y-intercept, sorry, the x value being 4, that would be extrapolation. Or you could substitute, say, x is 5, and that would be outside of your data set, so that would also be extrapolation. Alright, next up. it says different least square regression lines have different predictive power or strength. So Pearson's correlation coefficient, that tells you it's between -1 and 1. Okay, if it's negative, what does that mean about the gradient? It's going down like that. And if it's positive, it's going up. Okay, and then you have these sort of indicators here. 0 to 0.25, very weak. 0.6 to 0.5 weak. 0.51 to 0.75 moderate. 0.76 to 1 is strong. Okay. Then we can use our CAS to find the coefficient of determination and the R value, the Pearson's correlation coefficient. So the way you do that is you go Control left, alright, menu, statistics, stack calculations, linear regression A plus BX, and you put in your explanatory for the X list and your response for the Y. Okay. Sorry, my face is in the way. Okay. Can we see it gives us my A value? 6.3 gives me my B value. Gives me R squared. That's called the coefficient of determination. Gives us R, Pearson's correlation coefficient. It also gives you the residual values. Okay. So going back to here, in this example, we get R squared is 0.98, rounded up, and R is 0.99. Alright, so that would mean it's strong. And how would we interpret this? We would say 0.98 as the decimal. You would say 98% of the variation in the response, whatever the response variable is, can be explained by the variation in the explanatory, whatever that explanatory variable is. Alright. Testing the assumption of linearity, you guys need to do a residual plot. Let's do it with that CAS. Okay, go back to your page with the graph, and we go menu, analyze residuals, show residual plot. Okay. Alright, so this is, again, a very, very, very small data set. You're not going to get that in real examples, but if there are values randomly above and below the line and there's no clear pattern, okay, then you say a linear relationship can be used. Okay, so if the residual plot gives you random things above and below the line, then it is linear. If you get a curved pattern, okay, and sometimes you will, then you're going to need to use a data transformation, which you'll have to cover at another point in time. Alright. Now, can we see that that is the actual data point, 110, and it's below the line? Can you see that? That's why you have a negative residual here. If you hover over it, it gives you a residual of negative 0.33. Okay, so when x is 1, it's below the least squares regression line, because that's just the least squares regression line which has been tilted horizontally. And I believe the document also shows you that, okay? It says, example, at explanatory x is 2, the predicted is 14.33, if you substitute in. The residual is the actual minus the predicted, 15 minus 14.33, so you should get 0.66, and let's just check that. Okay, can you see that? Yep.